So before I jump into StyleGAN stuff for this week, were there any questions about the data set work and like other things? Oh, that's the wrong button, like always. Were there any questions about data set stuff from last week?
I had some like follow-up questions on like what makes a good data set, or what like appropriate ways to like bulk out the data sets that I have would be. Is now a good time, or should we maybe talk about
let's talk about it now. Yeah.
For sure.
So okay, so bulking out your data set. So how many images would you say you have now?
So I tried on a few different things. One of them was a fruit stickers Instagram.
Okay.
I was pretty quickly able to get about 1,000. Yeah, it's like I think it'll be really good.
Cool.
I was really quickly able to get like 1,000 images that were pretty high quality.
Cool.
But I'm wondering if there's any benefit to like rotating or mirroring.
Well, with stuff like a sticker where there's a lot of text, yeah, it's like you might want to rotate them, or you might want to flip them and see what happens. Yeah, it's probably beneficial to at least try the mirroring. Rotating, it just sort of depends if like you think the images are able to be rotated. So I know Esteban, you have a lot of like abstract work, which like can definitely be rotated in many different directions. So that's pretty doable. But like obviously you work on something like faces, you don't want to rotate it because like you don't realistically want faces going sideways. And like if you want to make a like a fake image, a fake face data set, and you want them to really look like faces, you don't want to like mess with stuff that much. So it just sort of depends on what you're trying to achieve or what you hope to get out of it. So I'd say like, I would sort of want to see the data set before saying for sure, like you definitely rotate everything. But my guess is that like mirror augmentation will generally work, and then like rotation may or may not work depending on what the images look like. Yeah.
My data set is like images of vinyl covers.
Okay.
Like vinyl record covers.
Yeah.
And so I'm just wondering like if that's too like much of the same, because I mean everything is like circular and has like a very hard border. And I was gonna do like post work where like I can crop everything to a perfect circle if need be, but like I'm just wondering if that's too little of a difference happening, or
yeah. So what I would probably say for something like that is actually to crop in on the labels themselves.
Okay. So like zoom all the way in.
Yeah, zoom all the way in on the label. And the reason for that is that at 1024 by 1024, like the actual size of the label might be like 300 by 300. Like it'll be pretty small when if you actually take the entire like 12-inch record. And then you won't like, the machine is only gonna learn really stuff within that region, and everything else will be a black circle. And it'll just like, I find you'll get better resolution, more interesting results if you really get that label itself, because you have more pixels to work with. That's sort of how I would think about it, because again, it's like anywhere where you have stuff that's like pretty consistently the exact same, it's just going to memorize that. But it's also like what you really are interested in is the label, and like I think what you're really interested in is having different labels, and like the more pixels you provide it, the more likely it is to produce interesting results.
Okay, so I shouldn't waste like the white, like the negative space.
Yeah, exactly. So like with a black record, which is like, you know, like this, and then you've got this other, like the label itself here, like you're just, all this is going to be like kind of look the same. And like you could basically like Photoshop the label onto like any other record, right? So what you really are interested in is this. And like, so basically the best way to do that is to make that as big as possible, like on the screen. I don't know if that's actually possible with your data set, because I know like, depending on what you pull in, like the resolution might not be great, but just like as close as you can get to the label itself, the more likely it is to be better.
Okay.
Yeah.
Well, we can talk about this further later on, but like the interesting part about these vinyl records are like the way that they did design, like, and the texture at the edge of the border.
Got it. Okay.
So I don't know if like it's worth just like putting it in and see.
Yeah, I mean, with a lot of this stuff, the best way to find out if the data set is really good is just to try it.
Okay.
I'm quite honestly often surprised where like a data set I think is going to be really good just doesn't convert well. And we'll actually go through a couple things to keep an eye on when you convert stuff. But sometimes it just ends up not being interesting, and there's reasons for why it could or could not. Sometimes you have to run it a couple different times, and there's like a bit of a noise or randomness to a lot of these things where like it'll, one time you train it, it'll randomly produce crap, and the other time it'll like start to produce something good.
Okay.
And it's just, so it's a little tricky. But I would say like in general, like try as best you can to get what you think will be a good data set, and then we run it. And then if it ends up not being, we can figure out like why might it be, or what was the learning there. So the other thing is like, I would say like, you know, maybe someone in somewhere like wants to train gradients and like just like a little gradient. And like I can tell you that that will not work that well in StyleGAN, again, because of those convolutions where it's looking for edges and it's looking for features. And a gradient has no features in the way that it determines it's looking for features. So that is like one of the things you learn about machine learning. Certain things just don't work because of the technology that's underlining like the system itself. So things with hard edges work better than things that are always very soft. That's just like a thing to know about like machine learning models in general. Because they're basically looking, it's not edge detection, but it essentially is looking at edges and how to combine edges with other features. Yeah, so it's just like something that you learn hopefully by like being in this class and not burning through a ton of models to like find that out yourself. But some of you learn just a little bit through trial and error, just like, oh, this didn't really work, or it worked in a way I wasn't expecting. And sometimes you just don't know why things don't work, and it can just be tricky. So
if that's the case, what happens if you work with black and white images and you have only shapes?
So black and white will generally be fine, but no, yeah, again, you need shapes.
Only black and white.
I mean, it'll work fine. Again, I think the question there is like, is it something you could make by hand that's easy? Like, is it, like, this is a big thing I think about with machine learning. A lot of times people will be like, can I produce something that looks like this? And it's like, you could also do that in, say, like a coding program like processing, right? And it's like, if you could produce something in processing using like random numbers or other things you could generate, like, it's much better to do that. Like, I know, like, so now everyone knows how to code those things, so it's a different question, but like, it's generally better to do that because it's much cheaper. It's just like, it's arguably free to do that, whereas like a machine learning model costs money to generate, and you should just consider like, am I training a model to produce less than better results than say like processing, or like the work that you're doing is like, someone could generate that with code, but I know you can't, but I still think it's interesting to see what your stuff would look like run through a model like this, right? Where it's like, I would say for you, it's like, it's probably hard enough to make any one of those images, right? So it's like, it is a level of effort where it's like worth trying to see like what would automating it do, or just like, or maybe it's just even like what would a machine do with these things. Whereas like if it's like I want to draw a square and I want to see if I can train a bunch of machine learning models on squares, it's like you should probably just draw squares in a drawing program, right? Like it's not that hard to like make a square. So just like I think this is like the good thing about this is like the level of complexity is worth thinking about. So really simple things, while maybe an interesting sort of theoretical model are cool, sometimes you'll find that like it doesn't actually produce a result that is like anything more than you could produce yourself. So I think that that's something to think about a little bit. I haven't heard anyone in this class talk about anything like that, but like just it's something to keep in mind. Any other questions about data sets?
Is it JPEGs or PNGs that are preferable format?
Honestly, I found it doesn't matter. So in general, JPEGs are better because JPEGs are smaller. So one of the things that we'll talk about today is like you have to get your data set onto paperspace. And if you use PNGs, your data set might be gigabytes worth of files, and uploading gigabytes over FTP is very slow. Whereas what I usually find is like a 3 gigabyte data set is like 300 megabytes in JPEGs. So it's just much easier. And generally what I do is, so in the datasets library, there's like a way to convert it to JPEG or PNG. Both of those are the highest like quality of whatever you're using. So even the JPEG isn't super compressed, but it's just much smaller because of the compression model. So
but if you upload JPEGs, does it recompress them?
No, it won't. It'll basically when you generate the images through like the generator, it always generates PNGs. But it's just, it might learn a little bit of the compression artifacting, but like at the highest quality setting of JPEG, that's pretty minimal. Whereas if you were to upload like 20% JPEGs, like it would definitely learn artifacting, it would definitely reproduce artifacting. Yeah. So yeah.
Is there a target file size for what you're uploading beside it being 1024 square?
No, not really. I mean, it's just, again, it comes down to like how long do you want to wait for those files to upload? And like, remember, you have to have your paperspace machine on and running while you're uploading stuff.
Right.
So at 78 cents an hour, do you want to wait 6 hours to upload a huge, high resolution PNGs? Probably not. So you want to try to figure out how to make it as small as possible and upload as fast as possible. If you have a really, really big data set, like say you have 40,000 images, what I would recommend doing is actually first uploading them to Google Drive or something like that, and then syncing between Google Drive and Paperspace. And I have some resources on how to do that. Basically, the reason that'll be faster is because it's really commercial grade internet to commercial grade internet. It's just really fast. So that would definitely be a better model. But generally, if you have 1,000 images, PNG or JPEG, it's not really going to matter that much. It'll take an hour at most. So it's negligible.
And it's 300K a photo, or will the output be noticeably different between a 50 quality JPEG and an 80 quality JPEG, or not really?
Probably not. I mean, I would say in JPEG, just keep it as, I would probably just say higher resolution than not.
Okay.
So I use 100% when I produce stuff as JPEG, which still makes them small because there is some, just the way JPEG compression works, it makes them smaller versus a PNG. So I would say in general, if they're JPEG, just make them as high quality as possible, and they'll generally be fine.
Okay. Oh, do you have recommendations for hard drives? Hard drives.
I don't actually. I mean, I think whatever you have is fine, because it's just sort of or go on Amazon and just search a hard drive and see what they recommend, and find the reviews and read through them, and it's generally fine. I have a bunch of Seagate drives and they're fine. They're all very they're all fairly inexpensive, so it doesn't really matter that much. I think hard drives have become they're such a good they're so good quality now that it really doesn't matter.
Okay. Cool. Thank you.
Standard and good. You can get a 3 terabyte for
such a good price. Don't buy. I mean, don't buy a weird name brand off of Amazon that's clearly half the cost of everything else, because that will be a bad drive. But in general, I mean, you can get I think I could buy a 5 terabyte hard drive for $100 now. It's way better than it used to be. So yeah, I would just say whatever other people recommend. I don't know if Wirecutter has a hard drive recommendation, but I would generally trust people like that, or just other expert recommenders on things. All right, cool. Let's do some StyleGAN stuff. Okay, so I need to figure out how do I move this thing. Okay, cool. So today we're gonna start by not just talking about StyleGAN, but talking about what the GAN stands for in StyleGAN. So GAN stands for a thing called Generative Adversarial Networks. What does that mean? That's basically this. So we talked about this a little bit in week 1, that there are generative networks and there are discriminative networks, and a GAN actually has both in them. It is basically a game that 2 networks are playing with each other. Essentially what happens is the generator is producing fake images, and the discriminator is trying to figure out whether those images are fake or not. And the way that works in, so basically this is how they learn, right? So the fake image will basically start by producing noise, the generator will start by producing noise, and the discriminator will clearly say hey, that's not the image that I'm looking for. Then the generator will learn to produce better images, and the discriminator will eventually be faked out, and then they will you'll tell the discriminator hey, actually you were tricked, and they both start to get smarter as you go through that process. So yeah, so it's just this is why it takes forever essentially to train these models, because it is a long process of doing this over and over and over again. So this is the common analogy you'll hear is between a counterfeiter and a bank teller, right? So we as humans can all tell this is not a real dollar bill. But for a reason, a machine bank teller might be I'm only detecting edges, so it looks like a dollar bill to me. And then you train the discriminator to say actually you need to start looking at color too, so it learns that. Now it's getting weirder, but slightly more realistic. And then we're getting to a place where it's clearly still not a dollar bill, but we're getting closer and closer. And this is essentially the process that these machines go through. It is like, so this was created about 5 or 6 years ago now with the theory for this. And we've sort of been like constantly optimizing this as we go along. And by we, I mean people way smarter than me doing machine learning modeling actually. But essentially this is how it works. And this is the analogy for the underlying system. So yeah, so in 2014, that was the very first GAN, and it was like 28 by 28 pixels, and now we're at much larger than that. So specifically to StyleGAN, like let's recap what we talked about yesterday, or last week, which is what does StyleGAN do? And it generalizes the features of training data to produce new similar images. So again, links to repos and papers if you want to read more about that. The inputs for these things are a lot of images. So like I said, around 1,000 is sort of the sweet spot we're looking at for like the minimum. And then the inputs when we're actually making these things are the vectors. We talked about vectors last week, and the output is an image. So I think we touched on this a little bit last week, but I want to talk a little bit more about it, which is like latent space. So when you hear someone talk about latent space, that is essentially this vector space that people are able to manipulate to generate these images. StyleGAN isn't the only one that has a latent space in terms of like being able to manipulate images and that sort of thing. It's been a thing that like machine learning modelers have made for like a while as a way to generate new images. Again, like an analogy to think about here is like this is basically someone taking this high latent space and mapping it down to 2 dimensions. And you'll see at the top here, like everyone, like or along this right side in the middle here, like at every one of these like color-coded things ends up being what the image is producing. And you'll see there's kind of some weird stuff going on, which is like, look what's happening with the 6s, right? They're kind of like doing this weird mapping through here. And that's because, I guess, what's this other color? So it's mapping around 2s, is that right? It's purplish. 2s and 1s and 0s. Okay, so like that makes sense, right? So a 6 could look like a 0 depending on how tiny its tail is, and it could look like a 2 depending on like how loopy it is or that sort of thing. So like you kind of see like these spaces are not discrete. Like they can sometimes have like a very weird sort of discrepancy, which is also why like sometimes when you're animating through these spaces, you'll see that like weird things kind of pop up. And it's because how these things are mapped is not always. It's not clear. It's not clearly categorized the way you or I would. It's clearly categorized the way the machine learned the model. And you'll see on the right-hand side here, this is sort of the output. And you'll sort of see again, like as you move through this space, again, it's sort of force map down to 2 dimensions. That like you get this area where like 1s can be tilted and kind of look like 2s, and then 1s like can actually look kind of like 7s, just depending on how they're drawn. You got this really interesting space where 8s and 9s get really messy and murky together. And then obviously 8s and 3s, and there's some like 5s popping up all over the place. So again, this is because like, you know, as humans, like we kind of understand what a 5 looks like, but a machine has to sort of like take all the edges and try to manipulate those things. And also, I mean, we get confused too. Like how often do you see someone like write a 2 and you're like, is that a 2 or a 7? Like, or what is that? Like, so, you know, it's actually not the easiest problem to solve just numbers alone.
Can I ask a question?
Yeah.
So is latent space and output, is it always the same? Or latent space is like a way to look at like the like training?
Yeah, so latent space is based on training.
Yeah. The
output goes into that training space and like tries to pull out the images out of it, right? Yeah. So like, as you train through things, the latent space will change over time because, right, it's like learning new pieces that it has to move around. But then generally what we're doing is when we have a model file, which we then generate images from, it's just taking whatever vector we ask for and mapping it to this space. Yeah.
And so if the input for this were just numbers that were just black and white, why does it produce like these ghosty lines if it's part of the input?
So some of that is just because, so like see how in this scattergraph image that there's gaps in the spaces? So it's basically, it's trying to like interpolate between those spaces.
Yeah.
So yeah, and like also there's other thing where like basically again, remember that these models compress data. So like they're basically uncompressing data, and when you uncompress stuff, you sometimes get blurriness. One thing you'll also notice with a lot of StyleGAN models is like, especially if you look at face models, all the faces, their skin is very smooth, and it's because that ends up being a place where it can compress some data. Because it doesn't have to like think, like you can get some freckles sometimes, but like you won't get like really fine details in like modeling of skin. And that's again, just because it looks at so many different models that it's sort of averaging things out of like, what is the maximum difference in a lot of these things? So similar things are happening here, right? Where it's like, it kind of ends up averaging and blurring some things to make it all fit into a fairly decent sized model. And again, like I think I've shown this a couple of weeks in a row now, but like in the first version, it worked, both these versions worked really well with faces, but StyleGAN v1 was not the best for anything that was not a face. And now in StyleGAN v2, we've gotten a lot better in terms of like how to manipulate like images that are beyond just like faces. See, excuse me, these were trained on the same data set. So you'll see like textures are much better, actual outlines and shapes are much better. A lot of times you would get like these like sort of again very blurry shapes, and they would just sort of be amorphous, and now you get a much better definition. So actually just yesterday, Runway switched their StyleGAN training from V1 to V2. So if after the end of this class you absolutely hate using Paperspace, you can use Runway's StyleGAN training model. Some of the stuff I'm going to show today you can't do in Runway, because it's like sort of like you need to get access to the code to really be able to do it. But if you're just interested in training some of these models, you could do it on Runway. It ends up being about the same price, and it's actually a little bit faster on Runway. So yeah, it's definitely available to you. And you can download the models from Runway. It's a little tricky sometimes, but you could always download them and use some of the other tools we have that I'll have available to you. Like do some of this other stuff with it.
Is the process in Runway to do version 1 and version 2 is the same? Like if you have a video.
There is no longer V1 in StyleGAN. Like they have just switched it all over to V2. So starting yesterday, if you start training in StyleGAN, it's just going to pick up V2.
So and you have probably like a video for how to do Runway V1.
Yeah, it's pretty much the exact same. I mean, they change their UI pretty frequently because they're a startup and they're trying to iterate toward, getting a better process. But yeah, it's really no different than the process we do. It's just all in a GUI. So it's all like you upload a video or you upload your data set to it. You choose what you're going to transfer from, which we'll talk about transfer learning in a minute. And then it just runs the process. It's got some nice tools that are actually better than what you could get through Paperspace. But in general, it's just like, how much control do you want? You don't like, there are ways to tweak certain parameters of your model that you don't get access to in Runway. It just sort of like, it does the default version and that's it. But it is pretty good. It's definitely worth using. So I would say like, if you are definitely not interested in terminal or other things, like it's definitely a model. It's definitely something to keep an eye on. Okay, so remember how I said that the way that these train, it's not gonna let me do this, is it? Okay, so remember how I said they start by training, like they're really dumb. They're like bad at discriminating early on. So what I want to show is like 2 different videos of what V1 training looked like and what V2 training looked like. So V1 training starts like this. It starts really, really pixely, and as it gets pixely, it like picks up new features. And then this is probably over a couple days on Paperspace. It gets smarter and smarter and smarter. So it starts off as these like very blocky shapes, and it's trying to discriminate between what is a 4x4 pixel look like compared to the 256 by 256. So that's how the discriminator learns over time. So it starts by just like downsampling your images to like 4x4 and then learning off that. And then as it gets smarter and smarter and smarter, it gets higher and higher resolution.
Is each cell of this like the same vector?
Yes, it's essentially the same vector. And it's essentially, so you will see this also when you start your training, is you will see that as it learns more, your vector space changes. And that means it produces different images than you might expect. So if you were to take one like that one little top left one and just like watch it train, you will see that it alters pretty dramatically over time. And that is again because maybe its vector is changing, or also just the entire space, like, or sorry, not its vector is changing, but maybe like the area around that specific vector is changing, but also maybe the entire model is shifting in different directions. And this is what V2 looks like. So in V2, instead of it being pixels, it starts as noise. And then the noise becomes a little more granular.
How do you capture this?
I'll talk about that in a minute, but it's basically like, this is just what it outputs while you're training it. So now it's starting to pick up like leaf featuring kind of things.
So this is like maybe like 1 frame per hour or something?
Yeah, about that, yeah.
Yeah.
So this is also a thing, right? Is you have some interesting things you could play with while you're working on it. And now it's like finally starting to catch like flowers and shapes and colors. And it's like, it's starting to, like, this is the thing about a lot of this stuff is it catches certain things at certain stages.
This process footage, is this a screen capture, or is this something that you can have running that exports once you're done training your model? How does this get?
Yeah, so Runway exports out this. This is just grabbed from like every JPEG that it spits out over 3 days. I just brought it into After Effects and like sequenced the layers and just,
Oh.
Yeah.
Okay.
But Runway does produce a video from their stuff, which is like cool to watch.
Awesome.
So this is like a very different approach from version 1.
Yes. And because of that, it actually works better, right? So like if you imagine like resing up from like pixels, like isn't actually the best way to learn features, but it ends up that at the time that was the most stable way. We'll talk a little bit about stability when I show some other things, but like now they've found a new technique that like maintains working through this like noise. And like now we're getting to a place where like, if you squint, these could almost look like flowers.
Yeah.
I don't think I finished that out, or maybe oh, you know what, it ended early. But like, these aren't perfect, but like they're definitely better than they were before. Oops, that happened. So like, you know, again, like this is a pretty interesting texture, right? Like this is like, these are like flower textures, but like they've obliterated the actual exterior shapes of flowers. So again, we're gonna look at a technique that like actually skips this step and makes training faster. But if you did want to do this from scratch, you could get stuff like this. But it's generally like, it just takes longer to train. So basically we'll look at a technique called transfer learning in just a little bit. And basically it saves you about a day or two of training time, which is pretty huge. So most people don't train from scratch anymore because of that training time change. I actually had to train this from scratch because in order to do transfer learning, you need a previously built model, and no one had built a model at a non-square 1280 by 768 before, so I had to do it, which sucked. It definitely took like, I think this training took like 6 days total to get to like maybe a little bit better level than what you see here. We'll talk about all that in a minute.
Is there a way to like look at the current state of training?
Yes. Yep. I'll show you how to read that and interpret that in a minute. Okay, so as I mentioned, there are some things to watch out for when you are doing training, which is there's a thing called overfitting. So we'll talk a little bit about overfitting. Overfitting is essentially this, if you think about the statistics of this. So what you'll see here is in all three of these graphs, they're just a bunch of dots of images. Overfitting is bad. Overfitting is bad, and the reason it's bad is because if we think about what we actually want to do in terms of a latent space, right? Like we want anything, a space in any region in this space to be a good image. overfitting is essentially memorization. And if I were to put a dot that wasn't on this red line, it would not give me a good image. Or it might give me a memorized space of something close by. That is bad because that's not the point of the model. And if you think about it this way, like you don't want to generate a model and spend $100 training it for it to produce the exact same images you already gave it, right? So again, this is back to this idea of like, what is the purpose of this? The purpose of this is to give you a interpretable space that has many different types of images in it. So it's pretty rare that you get underfitting. Underfitting is where basically the model like just picks out like a very bad way to train it, like of thinking about the space. What you really want is what's here in the middle, which is like, this is what we call generalization, right? So it's not saying that like, it's not perfecting like where exactly each one of these points is on this line or like generating a good, like it's generating a space that is an average or generalization of that material. So here are two examples of, so this is what overfitting on the left looks like. And then obviously this is compared to what you want on the right. So you'll see, I'll replay this again. You'll see that like, there's no interpolation between images. It just jumps from one image to another, right? It's essentially memorized. The reason this is really blurry is it was actually just a 256 by 256 model, it's very small. But like, so again, the idea is that you have a space where you can generate millions upon millions of images. This would give you like the same 50 images over and over again with very minor changes. And that's just not good. It's just like not really the point of training it. Now, as an artist, you might say like, I actually really like how fucked up this TV screen looks like. And like, that might be a reason to use this model. So it's sort of like, not all is lost, but I would argue like, I wouldn't want to spend $100 on this model, right? I might want to spend 25, but I can't really get that out of this. So like, overfitting is, again, one of these things where like, from a purely statistic model, like a data scientist can look at that, like we look at that and be like, that's really bad. As an artist, you might say like, cool, I can leverage this badness to do good things with it. But again, it's just worth knowing that like, overfitting is essentially, especially common when you have data sets of very small, like a very small data set. So in this example, I grabbed just like a ton of TV images and phone images and other things off of like Amazon, like just like product listings. And all TVs essentially are shot in the same 3 photos, right? Face on, like 3/4 view, and then like a side angle or like a back. So when you take thousands of TV images, like all it does is learn that shape, and it doesn't learn that there's multiple ways to do it, right? I think if I were to do it again, or like if I had the perfect world and like a bunch of TVs, I would put them on like, what is it, a daisy? Like what's whatever the spinning thing is? Lazy Susan, yes. Where did daisy come from? Anyway, like a lazy Susan, and you might photograph like every potential angle, right? And you might learn more about the model like that. So like overfitting is like a very common thing. If you are at like 750 images and you just want to see if you can eke by, keep an eye out for something like this. As I said, it's not terrible for art, but it's not great. It's not a good use of your money, essentially. This is what it looks like when you actually look at it as a grid view. And like, this is how you'll be able to check for this, is as you train, your model is generating this grid view. And what you can see here is like, if you just look at a handful of these images, you'll see they're super similar. And in a grid view, you mostly shouldn't have images that are that similar. Like if you look at a lot of these like phones, or like, I guess they're like almost big phones, which have like this like pink, yellow, and blue, you'll see that they're almost always the yellow is in the top right or the top left. So again, that's because of mirroring. But like in general, if I were looking at this, I would want to see one where like it sort of interpreted different color spaces in those areas. You'll notice that these laptops all look pretty similar in terms of their shape, in terms of their color output. So this is just the way to sort of keep an eye on this thing. Now, with this many images, it's pretty clear it overfit. If you have a bigger model, like a 1024 by 1024, I think it spits out like an 8 by 10, like an 8 rows and 10 columns or something. So you might think it's overfitting, and it might not be. So like this is where you might also want to do an animation to sort of see if it actually like jumps between those animated states. It can just be a little tricky to know for sure if it's overfitting just yet. There's a couple of reasons for that, but that's something to keep an eye on. Okay, the other thing that might happen to your model is what we call mode collapse. you'll know what mode collapse is because after training for it for a while, it just looks like total noise and mess. This is what mode collapse looks like as you're training it. So like one thing is it doesn't look at all like what you gave it as an input, right? So in this case, like I gave it flowers and it's like spitting out something that's pretty similar to the same flower, but like like in no way does it look like it memorized it, right? It's super noisy. You could say that there's some changes between these images, but like if I uploaded images that have like blues and yellows and other colors in them and I'm only seeing red, something tells me something's weird going on here. What this looks like when you actually do the animation for it is this. So again, this is cool as an output, but like it did not learn at all what it was supposed to, what flowers are supposed to look like, right? It's super noisy. It's got this very weird pattern. It is doing bouncing because it is sort of memorizing certain things, but in no way has it like memorized the images I gave it. So again, this is cool, like it's a cool output, but it's not at all what I wanted it to do, and from a data science perspective, it's very, very bad. This is actually, like again, you'll be able to tell when this is happening to your model, but sometimes you will worry that the early stages of your machine learning of your model will look like this, and you'll be like, I'm really worried it's collapsing. And you have to give it a little bit more time to see if it stays in a collapse. I don't really want to talk about gradient descent too much, but like essentially what's happening here is that if we think about these models in three-dimensional space, there are like all these like curves and humps and loops. And basically what a model is trying to do is it's trying to find the lowest part of a curve. This is the worst way to describe what we're actually doing, but basically like what's happening is it gets stuck. So like imagine that you've got a space, and I just want to tell you like, you've got to find the lowest point on any one of these models. We as humans would know that it's either this or this, depending on like how straight I drew this, but a machine might get stuck here. And when it gets stuck here, it hasn't really learned anything, but it also thinks it's at the lowest point, but it's because it doesn't see the rest of the space. So it gets trapped in this, and it also can become really easy for the discriminator to like, just be like, cool, that seems like the right image. There's actually a bunch of research in what is called adversarial examples. And basically it's in a classifier system where like, say you're training between cats and dogs, you can feed an image that has a bunch of data inside of it, like pixelized data that fakes out a classifier. Because of how these things are trained, they're trained to sort of like look for certain features, but there's like a hidden model underneath it that you can like fake it out with. I'll find a link to an article that has like a bunch of images of like, there's ways to encode data into an image to like fake out a classifier. But that's because of the system. If this didn't make any sense to you, just ignore it because I also did a really poor job of explaining it. But essentially like what happens is it gets stuck in like a single area, and it convinces itself that that is the model that you're trying to train it on. It doesn't make any sense to us because as humans, you're like, that's clearly not a flower. But it makes sense to the machine based on how it's being built behind the scenes. Okay, so actually, any questions based on what you just saw here? Like, are you worried about making GANs now, like anything like that?
Sorry, so about the getting trapped
Yeah.
in the wrong part.
Yeah.
I don't know if I missed it earlier, but so when the machine does get stuck on it, then is it a problem with the model, or do we have to do something again?
It's essentially a problem with the model, and the only way to fix it is to start over.
Okay.
Or to go, like, so basically you'll have like, you'll see all those steps of like as it's training, and you'll find a space where it like starts to like mess up. And what you might do is you might go back like a handful of steps to where it wasn't messed up, and you might start over again from that space, from that place.
You can like manually be like, come here and then do it again?
Yes, you can manually do that. The manualness is like digging into some code and like resetting some points. It is possible. There are also some theories around parameters you could change in your model to actually like fix this, but it's a lot of theory right now. We have like, what's very crazy is that most people don't know why mode collapse happens. Like we just aren't sure. We have theories that we know it's this, but like we're not sure why. We're like, there are many reasons why a computer might get stuck there, but like we're not sure exactly why. So it's a lot of people saying like, oh, I have a technique that fixes it, and then you try it, and you're like, that didn't fix it for me. Like, so it can be really tricky. I would also say like, if this happens, you like don't. It's not the end of the world. It obviously will cost you some money, and that sucks. But like, it is. You could again train the model again. Like clearly, I've trained that model to actually work with flowers, and like for whatever reason, in that exact example, it just collapsed on me. I think collapse happens somewhat often in a runway, like, and I just don't know why. I don't know if they changed the parameters or something, but I have seen that people get collapses fairly often in runway, and I don't personally want to use paper space. I don't know why. There could be a number of reasons why, but it is something to keep an eye on. Runway won't give you your money back if it messes up on runway, just like paper space won't give you your money back. So, you know, it is something to keep an eye on. It's like, so again, I had this student last semester that was like talking about pottery. It's like finding out your pottery exploded in the kiln. Like it happens, it just happens. And there's not much you can do about it. And you just say like, oh, well, it blew up, I gotta start over. So it's similar for this.
Using that same metaphor, like when your thing blows up in a kiln, you can like hear it smash sometimes. Like, is it possible for you to know when you're having mode collapse aside from just like checking the model as it's running, or like is there amount of time that it's like, okay, it's been 3 days, like it's been stuck at this one weird point, it's never going to get better? Like, is there anything that ever like looks like mode collapse but then actually just haven't given it enough time? Like,
yes, yeah. So I usually say give it about a day on the paper space machines. Like give it about a day and see if it comes back. Clearly that's like money you're spending and you're like kind of nervous about it, but generally I'd say like 12 to 24 hours you'll know if it's actually stuck there or not.
Okay, and on both paper space and on runway, you can preview as it's building, right?
Yes, yep, yeah.
Cool.
Speaking of which, I'm just gonna walk us through the steps that it takes to run StyleGAN. So I actually have a full demo video like that walks you through the exact steps like on paper space. And so I'll show, like I'll just post that video in our Slack channel. But basically I'll walk us through the steps, like just sort of like really quickly here. And the video will contain everything. Kirk, can I steal your power? Yeah, cool. So it's important to, again, remember the steps of training versus testing. So when we talk about training, that's when we're making the model. That's when we're like telling the machine to figure out how to produce this data. And then we talk about either testing or generating, or we might hear it called as inference. That is when you say, take this model and now generate new images from it. So training always takes place in paper space, or if you're going to do it on runway, it's in the runway system, and like you just go to training. But training always happens on paper space, again, because it takes forever to do. So you need a server that will let you run it for a while. So this is the video. It's here in the slide deck. I'll also post it in our Slack channel tomorrow or tonight. So it's available to you now to watch. Essentially, what the steps for this involve, like basically, like you take your file setup and you move your files up to your paper space folder. So you're going to move them into a folder that I would call like raw data sets. This folder probably doesn't exist when you open up your StyleGAN model in paper space. So you're going to make a folder, and then you'll basically put all of your images in one folder, and they have to all sit directly inside that folder. And you'll put that folder, and you'll move that up into this folder in StyleGAN. So now you've got all of your images up on paper space in the same folder where your model is going to run. The next thing you need to do is there is a thing that you need to do to create. So basically, the StyleGAN model does not read images just like as JPEGs. It has to be converted to a format called TF records. And the way you do that is in terminal, in paper space, inside your StyleGAN model, you run this command, where what's in yellow is just like the name of the folder that you're running it off of. The name doesn't really matter, but it's important to know that whatever your name you use at the .datasets / whatever this new folder name is, you're going to have to remember that and use that like going forward for the process. But basically what you're doing is you're converting all of these images into a new format that the machine can read. Basically, all it does is it takes all the pixel values and like collapses them into one huge thing. That's pretty much all it does. These files will also be big. I would not recommend running this like locally and then trying to upload these files, because some of these files will be like 10 gigabytes. So make sure that you like do this on paper space, because you will kind of go insane if you try to upload all those files.
So it's one file per data set?
It is not. It is actually, so so if you remember that pixel data, where it was doing stuff from pixels, where it was like, it starts at a 2 by 2, and then it moves up to like a 8 by 8. So actually what it is all the data for each of those layers. So you'll see a thing there called TF records 02, and that is a 2 by 2. There's a 2 squared. Then you'll see a 2 by 3, which is what, 8. So you'll see all that up to like 9, which is 1024 by 1024. So the 1024 by 1024 is huge because it has literally taken all of your images and like just taken a straight array of all the pixel data and like combined them. So if you have like 40,000 like images at 1024 by 1024, that TF records file might be 50 gigabytes, which sounds insane, but it is true that it might be that big. Okay, so once you've done that, once you've basically converted it, you're ready to train. That process of like actually converting your files takes like minutes at most, maybe seconds. Once you've done that, you're going to run another command in the command line that just basically says like, hey, I want to run training. The number of GPUs you always have on Paperspace is 1. And then you want to say like where the data set is or what the data set name is. This matches the name you put in for the new folder name here. So make sure that those match. I would recommend not putting a space in your name because it's just going to be like really confusing to find it. So do underscores or do whatever, but make sure the names match between those two. You will not touch anything else except these 2 commands. So basically you need to give it what the name of the data set is, and then you need to decide if you want to do mirror augmenting or not. So mirror augmenting is flipping it left to right. So basically set it to true if you want to do it, set it to false if you don't.
Does that mean you don't have to do it locally?
Yes. So when you make your data set, do not use mirror for StyleGAN because it doesn't need it. It has it built in. If you want to do rotations, do rotations in your data set. So you don't need to do flipping in your data set. That will just produce more data and like bigger files, and it's just not worth it.
That also makes sense for why you would only need 90 degrees and not like the full like 90, 180.
Well, actually, if you think about it, like you will get different images at each of those stages because of rotation. Because rotation is not the same as mirroring.
I guess the specific images that I'm thinking about tend to be symmetrical either this way
Yes,
or
that's
that
true.
way.
Yeah,
But yeah,
yeah.
that's
Yeah. Yeah.
What if you only want to mirror like certain ones? Then you have to do it.
Then you have to do it manually, and then you have to upload the manual data as a part of this, and then turn mirror training off here. Okay, so when you do that, it's going to kick off this process in your command line. The thing you'll want to do is you'll just let it wait for a little while. Unless you get an immediate error, it should be fine. This is probably after, I don't know how long it's after, but basically it's going to start putting files in a results folder based on the name of the data set you gave it. You'll be able to figure out because it's the only one you're going to have in there. But it'll start generating files like this. You're going to ignore all the TXT files, just like you don't need to worry about them. But then it's going to generate some JPEGs, and it's going to generate what are called pickle files. Pickle files are your model files. So that is essentially like the mathematic, what we call weights of your data set, or like of what it's learned. So again, if you think about how we had the layers in our neural network, the weights are essentially like mathematic representations of each of these nodes. That's all. You won't be able to understand anything that's in that file. Don't try to open it or read it. It won't be readable. But it's important to keep these files if you want to actually generate an image from them. So the fake files are what you can use to look at. So those fakes are like each time it generates a fake, which is usually about every hour or so. It'll generate a fake image. You can open that image and look at it, and it's going to be a grid of fake images. So very early in the phase, it's going to look kind of crappy. After a day or so, it'll start to look pretty good. And everyone asks, like, when do I know I'm done? And it's a little bit harder of a discussion to have. I've got some slides about that afterward. But essentially, you'll see here that you've got 1049 as a fake and 1049 as a pickle file. If you really, really like the fakes being generated from 1049 or 10491, don't delete that pickle file. If you, like, really early in the training, you'll kind of get some garbagey images. and you'll get garbagey fakes. You can delete those pickle files. Just know like you'll never be able to generate from that stage ever again. So it's important to know like when in doubt, don't delete a pickle file. If you chose like 100 gigabytes of storage data, you could potentially fill up your hard drive. I don't think you really could with StyleGAN. I don't think you're gonna fill it before it's done. But there is like you could maybe fill it if you just kept it running for a couple days or like more than 4 or 5 days. So sometimes I will go in and delete stuff I know I don't need. It just sort of depends on what I'm doing. But generally, like every 24 hours or 12 hours, I'll check on these files. And if you've seen it stop and hasn't generated an image in a couple hours, that's a sign that something's gone wrong. So maybe check every 6 hours just to be sure. It should generate images approximately every hour. So it's like just been an hour. Like don't sit there and wait. Like this is like a watch pot never boils kind of thing. If you sit there and wait for it to generate an image, like you're gonna like drive yourself crazy. You're gonna think it's broken, and it isn't. You just need to like let it run. So in general, like my process, like don't sit there and wait for every image to be generated. Like go on with your life and come back to it and check on things. Yeah.
Is training a finite process? Like can you train forever or it just stops training?
So I think the default is it stops after like 25,000 iterations, and you will never hit 25,000 iterations. Like that's like 2 weeks or 3 weeks. And it's just like generally like I find it trains before then and it's like cool, we're good. I did have a student last class who actually trained for the entire time. Like he spent more money and then whatever to get it. And like he personally thought the results did get better over that last week of time. When he showed me the file, I was like, yeah, this looks good. It looks a little better, but like I don't know if it's worth like training for an extra week. So in general, like you should decide like if you really, really want to see how far it goes, you can do it. But like I generally stop it after like maybe half that time. So yeah. Okay, so if you open these files, like you open very early stages of these files, you'll see something that looks kind of weird where it's like faces of people. Like if you're training this, so this is in a case where it's training on my floral data set. And like you'll see the very first step is this, and the next step is this. And this is what's called transfer learning. And transfer learning is like kind of hard to describe. The way that I describe it is like this. Let's say that I asked a young 8-year-old, like let's say I asked an 8-year-old child to write me a sentence in English. And I just said like, write me a sentence. And they could write a sentence and I'd be like, cool, that's a sentence in English. Now the thing is like, all I judged them on was on the sentence, right? But the truth is it took them 4 or 5 years of English classes or whatever to actually learn how to write that. So they learned a ton of other things in the meantime while they were learning. And that's essentially what transfer learning is that while we're running through the process of like these convolutions and learning things, it's learning not just how to make faces, but how to maybe make other shapes. So when we take another data set and we say, hey, learn this, it kind of already has a head start. It's like, oh, I've already learned how to make shapes that are like flower shapes, or already learned how to make shapes that are leaves. Like I already know what those shapes kind of look like. So this is a way to get a head start. It basically saves us about a day or two of training time, which can be pretty huge on something like Paperspace where it's like 75 cents an hour, right? So the technique that you're gonna work with if you work with my library is it will start with faces. And like, I think the first time I didn't tell anyone and they were just like, why am I seeing faces? I think it's broken. It's basically just that it starts with that face model that like NVIDIA made that's really big and famous. And it's like, they train that for like 30 days or a week or something. Like they train it for a very long time. So we're just gonna take that and we start building on top of it.
This is what you were saying will save us like a couple days.
Yes, it'll save you a couple days, but the thing is you will never see those other phases. You'll never see that noise.
Okay.
You'll never see those pixels because we're basically training from a model that already exists. So if you really want that weird noisy step, you have to train from scratch and just expect to like train it for more days than you currently are. And I would say like the way I've set up the cost for this class is like you basically like can do a model with transfer learning in the cost you have. So you should expect to spend more money if you want to actually get that noisy step. But you can, totally could. I have yet to, like there's some theory that maybe transfer learning creates not as good of models. I've never actually seen that really play out. Maybe at like a very like theoretical understanding it could, but I generally find that it works fine. So like the first step looks really weird. These middle steps look definitely weird. And then like maybe a couple steps after that, like it looks like it's a flower model, or it's starting to look like a flower model. This is like hour 1. This is probably like hour 5, and then by hour 10, you don't even see the faces anymore.
And transfer learning mostly works well with data sets of faces, or is it about just the size of this face database? Or like, say, like hypothetically, someone made like a 50,000 image database of like pigs, like, or just whatever. Can you like essentially use any data set for transfer learning? Or
yes, so the thing about transfer learning is it has to be the exact same size. So you have to train for 1024s. You have to train on a model that was already done on 1024. So that's why I use this data set, because it basically came for free because NVIDIA had already made it and had released it. So in the case of where I was saying how I have that model that's 1280 by 768, no one had a model that size, so I had to train one from scratch to do that. The other thing I'll say is that if you are transferring a data set that is similar, like let's say you're not doing faces. So like one of the common things people do anime faces. So if you were going face to face, it will actually train a little bit quicker because all of the stuff it's learned is like really close. So what I did for my model, that 1281, is I trained it on flowers, and I trained the next set on different flowers. So transfer learned from that, and it learns really, really quickly from there. It doesn't, at the end of the day, like the difference in time is probably like maybe 12 hours at most. So like, as long as you have the size, it will generally work. But if you want to save yourself like $10, try to find the closest existing model that is already there. And some people have put their pickle files up online. You can get them. I certainly have a bunch of stuff, so if people want to be like, hey, do you have anything closer to this? I might have something, and we can train off of that. But in general, it's not going to save you that much time. But it is easier to train from something that looks similar than it is to train from something very different. But at the end of the day, the most important thing is the pixel values or the size of the set.
So transfer learning should be 1024 by 1024 images.
Yes.
You should have your.
Yeah, so everything I'm recommending for this class is do 1024 by 1024 because of this. I might have a 512 model, or like I could probably find someone on the internet who has a 512 model, but like it's gonna be harder to find. So if you really can't do 1024 by 1024, we can work with that. But in general, like it's easier if you start from this size. Okay, so the question I'm always asked is how do I decide which iteration is best? This is like purely an aesthetic thing. But I'd also say like, so basically like we've got 2 data sets here, or like we've got 2 fakes, like fake outputs from here. How would I pick between these 2? Like for me, it's like fairly easy, right? Like if I want something more realistic, I'm gonna go with this latter data set. If I want something less realistic, I'm gonna go with this, right? You notice how there's like these weird vertical lines? Like that's clearly like not flower-like, whereas this has like vertical lines, but they're also like, they have some leaf pattern to them. It just really becomes like, what do I want to do? Like, do I want something that looks sort of like flowers, but is very different or almost geometric? Like this would be cool to use this data set versus this, versus this. So it's like, each of these is a different iteration, right? And each of these, so this is probably like 100, this is probably 200, probably 300. So the other thing I would say is don't look at like, if we go back here, don't look at these 2 and try to compare these 2. Like they're so slightly different that it's just gonna drive you insane. Like literally choose between hundreds of different hundreds, because seeing this is just gonna like, it doesn't actually, it's also worth remembering like these are like, what, this is 4 by 7. This is 28 images out of like a possibility of millions. So you try to judge that by like these 2 sections is a little bit hard, especially when they're right next to each other. Like, so in general, like pick between like 100, 200, 300. Like, don't try to pick from really close ones. Does that make sense? Cool, okay. So once you have like basically finished your model, and finish is like a theoretical question, like sort of to you when you think you're done, right? Like I personally would say like, cool, I'm done at this level because I really like how these flowers look. I see some realism, but I see just enough weirdness that I'm cool keeping it. Other people might say like, I want to train this all the way to see if I can get really close to realism. You might be able to, you might not be. It just doesn't, we don't really know. So I could train this for another week and I might get slightly more realistic looking images. Once you've done that, like then you can start generating images. And generating images can be done either on Paperspace, or in collab. And the way I recommend doing the deciding is like, if you already have Paperspace open and you just finished a model, generate some images out of it, because it's just fun to do that. If you are like, basically then when you're done, download those pickle files, right? Like download them, save them to a hard drive, whatever. Like you can then use them anytime you want to generate new images. And in that case, it would do it on Colab. And the reason you do it on Colab is because Colab is free. So like you just don't have to worry about it. It's about the same speed. It's a little bit more obnoxious to actually get the files up and do that sort of thing, but it's just worth it because it's free. So I have a whole video on how to do that in Colab. Here, you can basically just generate, it's like the step-by-step process of how do you, so there's a link to the Colab file, you open it, you have to upload your file, you have to change one line of code, and you can generate images from it. This will show you how to generate images, but also show you how to generate those animations. So again, that process of like generate 1,000 images and then go through the 1,000 images and pick out your favorites and then use those as points in an interpretable space, right? So like you could say like, I really like 2, I really like 4, I really like 10, and then I like 30. And then you can just basically say like, there's basically a piece of code that will generate an interpolation between all those. And if you add this first step at the very end, it becomes a loop. So that's how you get looping video out of this. So you can actually like, because this is where it starts and this is where it ends, and if you start and end at the same place, you have a loop.
Do you have a video for that?
Yeah, that's all in this. It's all in this. There's a demo video here. But basically the way this process works is like, this is the command you'll run. You're just basically running the generator. What you want to think about are how many seeds do you want. So seeds are, again, these numbers. These will always be the same. If you use the same model, the number will always be the same. So if you like generate image 1 and you really like image 1, and then you want to come back like a week later and use that exact same model and you want to create an interpolation, it'll always be the same number, which is a cool thing. It's very helpful. But basically, how many images do you want to produce to look at? So this will produce 25 images. You could actually say 1 to 10,000 and produce 10,000 images. Good luck trying to download that from Colab. It's just going to like take hours and days. So maybe do batches of like 200 or 300 images at a time. You can batch them, turn them into zips, and then you can download them. All that's in the Colab file. Truncation. So I talked a little bit about truncation last week as we were talking about runway. Truncation is a way of, and actually I have some demo videos of this later on, but truncation is how we think about realism. So basically the further away you get from like 0.5, so 0.5 will be like fairly realistic, 1.0 will be less realistic, and 2.0 will be like very unrealistic. And I have a demo of that, like I'll explain that in a second. But basically you do need to give it a truncation when you generate these images. And also it's worth noting that truncation and seed have to go together. So if you change your truncation value at like, let's say like 1, and then come back a week later and you try to generate 1 again, but you change the truncation value, you will get a different image, a slightly different image, but you'll get a different image. This is how you generate what we call a latent walk. This is basically that animation. So what you'll see here is you give it this command of generate latent walk. You tell it where your network is. This is the network equals your pickle file. That's all it means. It's your pickle file. And then you pass it in the seed values you want to interpret between. So here again, you'll see I started at 3 and I ended at 3. That means it's going to be a looping video. You then tell it how many frames you want. So frames is sort of up to you based on the frame rate that you generally, if you're in a video, like you might have a particular frame rate you want. This is important to keep in mind that frames plus this kind of equals speed. So if you have 200 frames, this is going to be a pretty fast video. If you have 10,000 frames with the same spaces, it's going to go really, really slowly between all those points. So that kind of that plus like the frame rate you actually generate actually determines the speed of your video. If that doesn't make sense to you, just know that frames equals speed, because this next line is how you actually convert that video, or convert all these frames into a video. And this defaults to a frame rate of 24 frames per second. So you can change that, but know that when you change that, you're going to change the speed of the frames you're producing. This will generate basically this will generate the video from it. This is the folder where these outputs go. This might change a little bit. So you just have to sort of remember that like this is your folder location, and you have to like remember to change your folder location so it matches. But it will generate files that are all called steps. That %05D just says look for a number. Look for the number that is five integers long. So this will produce a video. This will produce frames. This top line will produce frames that start at 0001, and then it'll produce one that goes 00002. Like basically, this just helps it know how to order the frames.
Is it 200 frames per like transition or
No,
for the entire
total,
thing?
total. So it tries to figure out,
Okay.
and it isn't always perfect just because the math might not work out. So it might be 204 frames, it might be 198 frames. So like just know you've got a little bit of wiggle room there. But this is generally frames for helmet for the entire length of the video.
And for the seeds, is there like a max? Like those are all less than 100, or like what's like the maximum?
There is no maximum to this. Remember that it generates a random value that is 512 dimensions, and it's between -1 and 1. And like, so basically, like if you were to produce 50,000 of these images and go through them one by one, you might eventually hit a place where like two images are really, really close to each other, but they'll like never be exactly the same, although to our eye, they might be exactly the same. So there's no limit to the number of values you can get here.
Oh no, more for like when you're inputting information to seeds, like you're using a number between 0 and 512, or?
Nope. No, it's literally, so when you go back here and you're producing your seeds, those seed numbers could be, it could be like 1,312,000,000. Like the seed really doesn't matter. All you're saying is like generate a random value, and I don't want to be able to go back to that random value.
Huh.
Yeah.
Okay.
Could it make a MOV instead, or?
Probably. This is a pretty high quality MP4. I don't know enough about MPEG to know how to change out codecs and stuff. The other option is this top line will generate a folder of frames.
Okay, so you could,
yeah. So this was an image, right? An image sequence that there are PNGs.
Okay.
So you could basically like just download that and bring them into whatever animation application you want to and convert it to whatever you want. Yeah. This is just an easy way, like you can do it all in one line to like get a video out.
And all of these is happening in Paperspace.
All of this is happening in Paperspace if you want it to. You could also do it in Colab.
Okay.
And again, the reason you might do it in Colab is just like you don't want to turn on Paperspace for an hour. You don't want to be charged. Colab's free. Basically, the reason that the reason we need Paperspace again is because we need a really long training time. Whereas Colab has like a time limit of like 6 or 8 hours. So you can't train a model in 6 or 8 hours. It's just not possible. But generating images happens in like seconds. So if you run this command, and I should have been clear about that, which is helpful. If you run this command will probably take 2 minutes to run at most. Generating images is very easy because all you're doing is you're saying, hey, take my model and just spit a vector into that model, and it spits out right immediately. There's no training, right? The training is that learning process of like, hey, is this a real image? No? Okay, well maybe we need to update so I can catch this next time, that sort of thing. So training takes forever. Generating images does not take forever. So we can use Colab to generate images as many as we want, and it's like you have a 6-hour limit, which you could generate like millions of images in that time. So it's just a different challenge. But like sometimes you might want to do it in Paperspace if you already have just finished training, because it's just easier to like. These commands are much easier to put in Paperspace. Whereas the Colab file, you have to upload the pickle file to Colab, which can take a couple minutes. You have to like run some stuff. Getting the zips out of Colab are also kind of annoying. There's just some steps that are kind of annoying, but it's free, so it like kind of pays for itself. The process for this stuff on Colab is in that video, so it will show you how to like do that stuff if you're interested.
Could you do this stuff in Runway? If you're doing the entire thing in Runway.
Yes. So yes, you can do the entire thing in Runway as well. And again, Runway you get that GUI where it's like a little, but it'll cost you, right? It costs you. I don't know. The training cost is always a little variable, just based on like how long you're training it for and some other things. But then so training is actually not 5 cents a minute in Runway. I think it's a little bit cheaper than that. But like it'll tell you an estimated cost when you train on there. But then once you want to actually generate images out of it, you'll get that like vector space you can sort of play with and whatever, and that will cost you 5 cents a minute. Okay, so that's sort of the whole process to generate StyleGAN. Sounds really simple, and it kind of is, but like the length of time it takes is a while. So length of a while for training is a while, and it'll just be like some steps to generate images. So I'm going to talk a little bit about some advanced stuff that you could do with StyleGAN. I don't expect anyone in this class to do it, but if you're really, really interested in one of these things, I can help you with stuff. But there are like, one of the cool things about StyleGAN is that there's a community around it. Like people are sort of like constantly like messing with things and trying to find out new stuff they can do. So it is sort of like there's a cool community where there's like new stuff happening all the time. It's a small community. It's like probably like, of the people I know on Twitter, it's like 20 people. But like I think it's growing more and more. And I think as Runway gets more up to speed, I think more people get interested in those things. So truncation, I talked a little bit about this. This is a video that shows how truncation works on my flower stuff. It starts at truncation, I think, at 0.5, and it goes up to 1.0. So you can just sort of look and see what happens. So that looks pretty like regular, and now it's getting to a place where like these flowers and the leaves are definitely looking like not flowers or leaves. I'll play this again because it's pretty quick. So this is the exact same seed, and all you're doing is changing the truncation value. So it is changing quite a lot between that. I think what's actually easier to understand is to look at this with a super weird face. So this is a face data set where we're changing the truncation value on it. So again, it starts and like you're sort of like, cool, this makes sense. This looks realistic. It's looking a little bit less realistic, and then it goes into like hell zone, right? Where it's like super weird. So this is probably 0.5 up to like 1.2 or maybe even larger. So when it really hits past 1.0, it's going like kind of into crazy land. So just be aware of that. You can explore that. You can experiment with that, but like it's worth knowing that like if you get too far out, like especially with stuff like human-looking things, it's going to look really, really weird. So that's truncation.
What does truncation stand for? What does that represent?
It's like a mathematic it's like some mathematic properties. Generally, the way I think about it is that if you think about a latent space, if you truncate the entire latent space into a smaller set, you will have more realistic stuff in the centers, weirder stuff at the edges. So basically, you're just saying like compress this space, and I just want like what's in this box. That's not really what happens, but that's like how I would think about it. Yeah. Okay. So there are some things called multi-data set training. As you noticed with transfer learning, you get that weird middle step of where it's like half people faces and half flowers. And some people really like that look, right? So like you could exploit that by actually picking that pickle value and just generating images from that. And that's something pretty commonly done in a lot of the art world right now, which is like, these are different data sets that have been trained like for a very short period of time on other data sets. So I think this one is like Simpsons, Pokemon, and some other things. So just like been constantly retrained on like new models, and you get these very weird sort of abstract shapes that like sort of like humans, sort of don't. But this is a fast process, right? Again, like we can do this on Colab. We could actually do this on Colab, which is why a lot of people do this, because it only takes a couple hours to get that weird intermediate step of a pickle file. So basically what they're doing is they're training it, like, let's say they trained it all the way onto Simpsons, then they trained it on the Pokemon, and they trained it on something else. And that whole, like, the intermediate steps take a couple hours to do for each of those. The one on the right is like between faces and anime, or faces and art portraits. I'm not entirely sure. And then this thing down here is actually like, I should forget exactly what this is, but this is like a couple different training iterations. This is probably like Japanese art, and then like cyber art, and then something else. I don't know. Like, but basically these are ways to, again, if realism is not what you're interested in StyleGAN, there are ways to sort of manipulate and add new things to it. So like another technique is, I think we talked about this last week, is like you could train this on a video, right? Like you could take a video, spit out all the frames, and have it train on StyleGAN. I think I showed this last week, but essentially like what happens is like StyleGAN does not interpret time. Like it doesn't actually know how time works. So what it does do, this will load. So it sort of like is like a weird interpretation of time, right? It doesn't actually understand that like waves start at the top of the screen and then come down. It sort of like sits in the middle and like moves things backwards and forwards in time. It's a pretty interesting look, but know that when you feed a video into a StyleGAN data set, you will generally get something that like looks exactly like the video you produced and will just like weirdly warp through time. That's generally what you get. This was something I think Kishu Yuma was the first person that I've seen do it. But again, this is that sort of thing where like you can kind of understand what the video looked like, right? It was like something like this or like this, and then it like produced these really interesting sort of like semi-realistic hands that are like morphing and doing weird things. Okay, the next technique is a thing called projection. Projection, I think I showed this in week 1. So how does projection work? So projection is the idea that inside of this space are millions upon millions of potential images. So what this does is it says, here's the image I want you to find in this space. So you give it this image, and it might try to start the image here, and it just checks this against all these other places. So it moves it around in space until it finds its closest result. It's basically doing a bunch of math to figure out how different the image is from the image that it's finding in the latent space. You will never find the exact image in your latent space, but you'll always find something that is a close approximation of it, right? Like these clearly are not the same image, but it's pretty interesting that inside of a model trained on thousands of faces of real people, that there's something that sort of looks like Mario, right? And again, that goes back to what I talked about with transfer learning, which is like these models are learning way, way more than what they actually represent when they give you an image, right? So like if you were to actually look at the value for this, the value for this might be like a really, really like it's very likely probably like again if you think about the edges as being like less real, it's probably somewhere here at the edge. And it might have a truncation value that's like fairly high. But it does find it because, again, it learns so much else in this model. And that model might have some weird corners of its space where things like this are represented.
Can you produce like a video that just kind of like hovers around Mario? So like right now we're starting from like the edge and we're going closer and closer to Mario. But then can you just produce one where it just like kind of rolls around? Okay. Yeah.
So basically what you can do is when you animate, there's a collab notebook of how to do this. Basically what you do is you give it an image and you say, find this image in the latent space. When it finds the image, it then tells you what that vector is for that. And then what you can do is you can take that vector, and you could say like, do a circle around this vector, or animate like in the space of this vector, right? So you can actually take this vector. Actually, let me show this. I think this is the next thing I have. So here is something that I've done, which is finding Oprah inside of the FFHQ vector space. So that's clearly not Oprah, but like, if I were to show that to you, like really quickly flash up and be like, who is this? You might say Oprah. So I did that for a bunch of different celebrities. And I took every one of those vector points between when it found the celebrity and it said, here's the vector point. So I'd say, okay, here's Oprah, here's Bruce Willis, here's Jennifer Aniston, and here is, who else do we do? Britney Spears. So I said, okay, give me those 4 points and now animate between them. And that generated this. So there's Oprah. There's Jennifer Aniston, I think.
So this was the source, one
this
of the sources.
Source, yeah. This is Bruce Willis. As he loses his hair, it's super creepy. And then that's Britney Spears. and it goes back to over at the end, so it's looping. But yes, so you could always get this vector, and then let's say like here's the Mario vector. You could kind of, it's not actually like, because it's not two-dimensional, it's a little bit harder to do this, but you could say, I want to go around, I want to do this. You could kind of do that. What you would probably need to do is actually just add some random values to your vector space, and it would kind of produce that. Yeah.
Were there more like well-known experiments with like finding faces in this?
Yeah, lots of people have done stuff like, there are lots of people doing that. Like that was like, again, like I always describe it as like a fart apps of the month. Like that was for a week, that was like the thing everybody did. The person who did the Mario one did like a bunch of other like they did Pokemon characters, they did a bunch of other things. I did one that was like, have you seen, there's that Aphex Twin cover that almost looks like what it produces here. I took that Aphex Twin cover and put that in the model, and you found something that was sort of similar to it. So there's like a bunch of like, again, it's sort of like the art gag type of thing that people have been doing with these. But I don't think I've actually seen anyone do this technique before, which was like the find a bunch of people and then like animate between them. What I did obviously for the SSHH class was like, then I also stuck it through a StyleGAN model. So then it was my flowers on top of it. And then we had people guess to see if they could figure out the celebrity. Okay, so this is based, like I've done this sort of in like order of easiness to hardness. So truncation is very easy because it's built in. Getting to like the projection stuff is doable, but it is like manually like laborious. Now we're looking at non-square images. So for this class, I would prefer if everyone just did 1024 by 1024 just because it's easier. But you can do non-square stuff using a different library. It is just like, it's tricky. It ends up being, it might not actually work on the P5000 because it ends up requiring a little bit more memory. So we have to play with it. But if you do have something that generally just will not work for square images, like we can probably work with it and figure it out. So if you're really, really interested, we can look at it, but I would generally say stick with squares for this class. I'm going to record a video the next week or two that shows how to do this using non-squares. So if you are really interested, you can. But just know, like, essentially anything above 1024 by 1024, which is like what I've been doing, if you want something higher resolution, your P5000 will not work because it requires more memory than that. So there's a P6000 on Paperspace, but it is $1.05 a minute, or an hour, sorry, an hour. So that is very expensive. So it's an option, but like just know it's, you really would have to really want it because it's going to be costly to do it. This will also work on transfer learning. I have a couple models of various sizes, but like I don't have all the sizes. So there's particular size you want, like I might not have it, and you might have to train it from scratch, which is a longer process. So lastly, just this week, I've seen, like, I started playing with some things, which is like, you can interpolate between two different models, which is like kind of mind blowing because like how that math works is very weird. Like, let's say I have a model space here and I have a model space here. Like, how do I go from this model to this model? Like, that's pretty crazy. But someone has a collab notebook that does it. So this is actually an interactive demo where they go from people that are anime to people with cat ears. I think I don't know. I tried this with some of my own models and I found it did not work at all. So your mileage may vary just depending on what you're trying to do. I think my guess is that because these are faces, that the face stuff just works better. In part because of transfer learning. So I know this is like a model transferred from another model, and like it probably kept some various things from it. Whereas, so depending on how different your model becomes, it can be hard to track between those two. I thought this was cool. It looks cool, but like, I don't know that it's really possible for most of us, especially because you have to train two different models to do it. But also, so there's also code for this. There's a collab notebook that I wrote based on the previous design artist's work. But what I like about this too is like these sliders to be able to change things. It's pretty interesting, and it could be a technique that you might want to use just to like look at your own images. So changing the seed, which is the top thing there. I don't know what scale does. I have no idea. There's something in the. I have to look at the code a little bit better. But there's a transition that you can also play with. So it might be an interactive way to look at it, and it's on collab, so it's free. You have to like upload your model to it, like change a line of code in your code to make sure it points to that model, runs some stuff. But then it's like, also, I think his is smaller than 1024 by 1024, but there's a lot of lag time as it regenerates images, right? Because it takes a couple seconds to generate these images. So sort of like reloads the image, there's a lot of gaps. So it's not as clean as this is shown to be, but it is pretty interesting. And lastly, I don't think any of us are going to do this because I haven't done it. It's very hard to do. There's a thing called feature manipulation. People have done this on faces, but it's really hard to do on non-faces for various reasons. But basically, this is how Mario Klingemann has done the making Mona Lisa smile. And then I did the same with like Kehinde Wiley's Barack Obama.
Now you can do it with this model in Runway, no? There's a source and there's a...
Yeah, different technique, but it's the same idea, or essentially the same idea. The way this works is, so if you remember how in that very first latent space image I showed you, let me go back a while. Really far back, damn. This one. So if you notice how, again, I talked about how the 6 doesn't always warp to like a normal space. Basically what you do is you train a classifier to learn where each of these images is in space. So like say I have a classifier for 6s, right? So I'd find where all the 6s are. Now, obviously this is a number model, so it's like pretty basic. But if you imagine that for smiles, right? So find all the images that are smiling in this model. You might not get a straight line. You might get something like it's curved like this. But now, if I put any image and I find any image of a face I like and I want to make it smile, I can manipulate it on that curve that matches the smile. So the reason this is really hard is you have to train a classifier, which most of us don't know how to do. Then you have to actually like do the math to figure out what that line looks like. And then you have to take that line and manipulate it into your space. But it's a technique, and I think someone will probably come along and make this much easier to do, or they'll do something like what you talked about, which is like, you can do it with your face poses. But you could technically do this with any model, right? So like in my flowers, I could train a model to like, or I could train a classifier to know green or to know yellow flowers, red flowers, and I could take any image that I like that is yellow and convert it to red. But I have to do the work of making this classifier, training the classifier, figuring out the vector space that manipulates yellow to red, if I could do it. So that's sort of like a very, very, very advanced mode of how feature detection could work, or how changing features in a StyleGAN model could work. That is super like experimental, and like I would not expect anyone in this class to do it. But if you're really into code or you're really into math and like want to try it, we could figure it out. But that's basically how it works. There we go. 8:30. Damn. Okay. That was really fast. So what are the questions you have about StyleGAN?
That number mod thing was so the training was on like many different handwritings?
Yes.
Or just 0 to 10 and that's it?
Well,
0 to 9.
All numbers are zeros, nines, right? So like,
but if you need 1,000 images. So
that's a famous model called MNIST. It is like basically been the classifier de jure of since the 70s. So basically, it's what all of our banking systems are used on. So it's how it does character recognition of banking stuff. Basically, like MNIST has long been like the data set that you can run something very quickly on to learn if it's good or not, right? Any model that could classify MNIST better than the current state of the art is like something that people want desperately. So I think MNIST started at like around the 70s. It was probably like 80% accurate, and like there's now models that are like 99.99% accurate.
So is this what OCR is based on?
OCR is meant for like non-handwriting stuff, right?
Right.
Yeah. So this is like handwriting recognition.
But OCR, like in theory, works on all like fonts.
Yeah.
So
yeah. I think OCR is not a machine learning model that I know of. It's like sort of like more algorithmic, and tries to figure out shapes via algorithms. But I mean, there's a lot of different machine learning models that are probably working on that, and whether or not their OCR is, I'm not really sure. There's a lot of stuff that's like half machine learning and like half not, and it's always it's always unclear to me like what exactly the level is between those two.
You do like a quick recap of how the process works.
Yeah, so
Just to
so the process how it works. Let me rewrite this on the screen. Sorry, remote folks. I'll take photos of this so you guys can see my chicken scratch handwriting. But I'll write this out again. Actually, let me just do it here. Let me just make a new slide. Okay, so the steps to do this are one, you need to move your images up to paper space.
there's a video for that, right?
There isn't actually, I don't think. Basically, you need to use an FTP client. FTP client will there is a video about how to set up your FTP client. And you'll basically just upload that folder into your paper space model. I can record a video for that because that's something that would just be helpful to people. But yeah, so basically just record, you'll basically just upload your files via FTP, or there's other ways to do it, but FTP is kind of the safest. Yeah. So you just upload it up to that. The next step you need to do is you need to convert your files to TF records. And that's one line in paper space in terminal. That'll just generate a TF records. The next is you need to run training. That is again one line of command, but like you need there's now like there's this, which is like wait 3 to 5 days. So like this is like once you've run this command, you just let your machine run for a while. It's going to run on paper space for 3 to 5 days. It's going to start spitting out these images. You can look at them, you can check them, see how they're going. But at some point you'll be like, cool, I think this looks really good, and I'm done. When you're done, then you just need to run, then you just need to generate images. And generating images is one more command line. And then it's sort of like, once you generate images, you're like, maybe I'm done. Maybe I just want images. Maybe I just want a bunch of random images out of this. Maybe I want to do animation. Like, so there's a bunch of like techniques after here. So it's like single images, animations, like all these advanced techniques. Kind of need you to already have a model.
Between 3 and 4, you can check the like status images.
Yeah.
Right, while you're waiting.
And also, I should say, like while you're waiting, you could download a pickle file and just play with it in Colab, right? So you could download a pickle file. You're like, I know this isn't finished yet, but I want to just start playing with it and see what happens.
While
it's training, right? Yeah. So training is like just a thing that like it's going to take over your paperspace server. So one thing is you can't train and test at the same time on paperspace because of memory usage. StyleGAN just takes up all the memory usage on paperspace. So just like you'll have no memory usage to actually test images while it's running, while it's training. So what you could do is you could download a pickle file from the paperspace, bring it into Colab and test with it there. Like make some images, see what happens.
But you can do that while it's training, download pickle files.
Yeah. Because that's like there's a difference between GPU and CPU.
Yeah.
CPU, you can do whatever you want. You can just download stuff. You can do whatever you need to through FTP or whatever. The GPU is taken over. So like you can't like basically if you were to try to watch a video like on your paperspace machine, like in the desktop view, it would probably be super laggy and it might even crash because literally StyleGAN takes up like 98% of your GPU. So yeah, that's like yeah. So but basically you can download files while it's running pretty easily.
So there's no reason to use the desktop view in paperspace, right? If you connect via like either terminal or FTP.
Yeah, you don't. So if you connect via FTP or terminal, you don't need to use the desktop view. If you are still struggling with terminal or just like don't want to, you can use the desktop view. Running these commands, you'll still have to run the commands in the terminal in desktop view. But if you want to move stuff around, like if you don't really understand FTP or whatever, you could open the desktop view. You could upload your files to Google Drive. You could open them in desktop view and then download them there. It works fine. It's probably a little slow. It's a little weird, but it would totally work.
So in what scenario you would run terminal in the desktop view?
Only if you don't like SSHing into your machine, which maybe you struggle with that, or like maybe it's just difficult. Yeah. This also reminds me that I had a student last class who wrote all of this into a document, and I need to share it. So in here, there is, this is my repo of StyleGAN 2, and in here there is a usage.md file. And my student Steve Olson wrote this up. There's a link to the video demo. These are all of his, like basically his way of how to actually get stuff. This shows how to do what is this? Yeah, so he's using a technique where he's zipping up the file, uploading it to Google Drive, and then using a thing called GDown, which downloads it directly from Google Drive. The FTP version also works, but this is how he did it in using Google Drive. So he has all of his steps here outlined. He also talked about, this is the custom data set way to make it. Here's how he did run training. You might have a question about how to actually quit your training process. This is outlined here. So you run this thing called NVIDIA SMI. I need to record a video for this. I will do that this week as well. This is a way to just like in command line kill your training command. It's fairly straightforward once you memorize these rules or like know what this does, but basically this is what you're doing. So that's how you go start to finish just training to ending. We need to add some stuff for testing. We never did that, so I can add that this week. But essentially those are the steps. Yeah, I'll share this in the Slack.
Is there a specific folder you need to upload the data set to?
Yes, yes. Actually, I can show you well, it's not specific in the sense that like there's a right one or a wrong one. It's that when you run this command here, you need to start with like this has to be the correct folder. So like you could upload this to whatever folder you want to, but you have to make sure you reference it correctly.
Yeah.
And then you have to make sure that this needs to be the right place. So this always needs to go to StyleGAN2 datasets, and then whatever your name is going to be.
Which one of these already exists in the file structure? StyleGAN, is that a current folder?
StyleGAN2 is a current folder. Datasets probably exists. Raw datasets might not. And then you'll need to upload, this is the folder you're going to upload. So you need to upload it to this folder and then make sure you reference it correctly. And this is where it's going to generate those TF records files. So I can just quickly show you, this is one of my models. So again, in here, like what you'll see is I have a folder called raw datasets. Inside of this, if I haven't cleaned it up already, are a bunch of images. Inside here, you'll just see these are all raw, probably JPEGs. Yeah, so just a bunch of JPEG images. These are 1024 by 1024, I believe. Yep. What that does is once I run this command to convert these to files, it then creates a new file inside of dataset. So you see, like I have a new thing called Crystal 1024, and inside of here, this is a custom model, so it only produces one TF records file. Yours will probably produce multiple ones. So that is now where the TF records are. When you are actually running a command, it'll create a folder called results. Inside of that results, you'll see this like numbered system. All this is it's saying what the folder data set it looked at does. So it's like they number them just so you know like the order in which you did them in. StyleGAN2, which is obviously the model we're working on, and then the data set name is there. And there's a thing called config-f or config-e, which you don't need to worry about. Just use config-f. Like that's all you ever need to do. I think by default it's set to that, so you don't ever have to change that. But basically, like, and then inside of these folders, each one of these is all of those fakes and those pickles. So that one doesn't have one, because I may have cleaned this up already. Yeah, this one has stuff. So inside of here are fakes, inside of here are pickles. You'll notice in this particular example that each of these there's one pickle for every fake. So I recorded a video last week that is how to do the mixed model training, and this is a good thing to do for mixed model training, because it happens so quickly that you don't want to miss one of those good steps. I think all of your defaults are set to 4 fake images for every pickle, which means you'll get a pickle every 4 hours instead of every 2 hours. That's just to save on like hard drive space. You can change that if you really want to, but again, because you're supposed to pick between every 100 like steps, like generating more pickles isn't really that helpful in this particular example. So, but like because of transfer learning and the mixed model stuff, you want it in the early stages. You want like more. You want a lot of pickles. So that's just you can change that inside the code. All that is probably like not worth worrying about right now. Like it's what the defaults are is good for you. But you'll see, like I do a lot of custom stuff with things in here.
Could you show the things? I'm very curious.
Yeah, what are these? These are so these are like these like oily blotches things. These are pretty big files, yeah. Yeah. And this might be a transfer learning model. Let me see. What did my index look like? Yes, so this is a transfer learning. So I started with these flowers, and so let me just open all these at once, and let me just look through. We can just step through them. I'm just going to load all these. Actually, one. Good here. What are we doing? Cool. Okay. So it started here. Make this bigger. So it started here. The very first step was this. So you'll see like the difference here is like it's kind of getting a little muddier here. Some of the colors are changing, but it's not that different. Jumping to here. So now you're getting more of these like sort of darker, deeper colors. Some of the shapes here are getting like pretty messy, right? Like it went from this to this, and now we've got more steps where like the flowers are basically starting to be eviscerated because they're just turning into these blobs. And then as I get further along, it basically gets to a point where it's like almost unrecognizable as flowers. So it was trained on these images.
Sorry, you. Oh.
So this is the data set it was trained on. What it started with were these, right? So it's like actually very quickly moving away from flowers very quickly. But you get those early couple steps where it's a little bit of both, and that's like an interesting sort of style. I actually think let me see if I think I have a video of this.
Are those photos from Google Earth?
No, they're actually just from like an artist who makes a lot of like weird oil drippy things. So I try not to really show, the final outputs because essentially like kind of stealing his work. But I use it to like do this type of work.
But does he make like hundreds of them?
Yeah, he makes a lot of them. I mean, he's like very prodigious. Oh God, this was like 2 days ago. So of course it's like 1,000 tweets ago. Yes, it was this. So this is what the video ended up being, right? So it's like one of those early steps where like it wasn't really that different, but it has a little bit of that sort of like texture, like it almost looks solarized, right? And all I did was I pulled out one of those middle pickle layers, brought those down, and then did all the same work that I would normally do my other work with that pickle layer. Yeah.
Only with one pickle layer.
Right. So the pickle is your model. Like that's the latent space. You download the pickle, and then you generate images by picking points in that pickle file. So this pickle file technically contains all of the data about what it has learned in your space.
Data set question. So if a lot of the images in my data set look similar, would the machine see this as like a priority and produce more that look like that than others?
In my experience, yes. Or like, what will happen is that the cluster of images that look like that will be bigger, right? Like that might be this, and then the other images might be over like out here. But it will sort of prioritize, right? It's like a statistical model, right? If you have a lot of data in one location and like a little bit more data in other locations, it's going to prioritize the data you're giving.
So is it better to clean those out or to have more images with those?
It depends what you want the model to learn, right? It's like you want the model to learn that in most cases an image should look like this, but in a couple random cases it can look like this. That's fine. So one of the things that I will generally do with video is in video files where you get a lot of scenes where they might be the exact same. Yeah. So there is a data set tool that I have a demo for that does fuzzy matching. Like it matches images that are close to each other. And I might go and like, there's a way to just dedupe completely, like find the exact match. But there's a little bit of fuzzy matching you can do as well. And it just depends on how different the image is. That you could eliminate some of those images that look really close to each other by cranking up sort of a value on it. The problem is it might get too greedy and then it like takes your image data set and cuts it in half. Like so you have to sort of play with it. But yeah, so I would say in general, like it'll learn what the data you give it, basically. Yeah.
So is it better to use this fuzzy thing or to kind of, if I have a video and like right now I exported it like 7th of the frame rate.
Yeah.
Like that. So
yeah.
is it better to do it like export the full frame rate and let the like fuzzy thing determine what's repetitive or do it myself? Or?
I would generally say if you have the time to do it yourself, do it yourself. The fuzzy matching is literally going to like sort of map images over top of each other and figure out how closely aligned they are. And that means it'll miss certain things. And or like if you crank up the rate to try to get more matching, it might actually match things that you don't want to match. So in general, I would say like manual will always be better. Like the human eye and actually just going through every image will always be better. It just depends on how much time you have and like how willing you are to like do that task. Cool, so I can stick around for a little bit if you want to look at data set stuff. Basically, your homework should be to keep working on your data set. And if you want to start training, you can. I know, like, Esteban, I know you're close, you're ready. So again, I want to reiterate, like, the point of this class is that by the end of the class, you do have a model, or like you have something that you're working on. I don't expect anyone to like have all the homework done every week. Especially because the data sets is the hardest week. Like, that is guaranteed like the hardest thing to do. Like as you saw, the steps for this other thing are like fairly straightforward. It takes a little while to actually train stuff and wait, but it's not the end of the world. It's like fairly doable. So I'm aware of the data. Like that's why I taught data sets at week 2 because I know it's going to take full time to generate everything. So if you have data set questions, like definitely please hit me up. If you want to look at stuff in class, like I can stick around a little bit. If you want to talk about stuff outside of class, like please let me know. I'm happy to schedule some time. And then yeah, like try StyleGAN if you feel like you're ready. If you're not, come in next week and I can like sit down and actually do the steps with you. The nice thing about it is like from uploading to making the records to starting the training takes at most 30 minutes. So if you want to do it together, like if you're like, I'm just not sure, like we can press the button together. That's totally fine. I'm also again happy to like do it over screen share like this week. Just let me know if you're like feeling nervous about it. And then yeah, I mean again, like next week we're gonna learn how to do next frame prediction and how to do style transfer. So again, I'm just gonna keep throwing new stuff at you. I don't expect everyone to like just follow along completely and be able to do it every week. But again, it's just sort of like, I know at 5 weeks with you, so I'm going to spend as much time as possible doing it. Next week, we're going to look at next frame prediction and StyleGAN or style transfer. The last week, I'll sort of leave it up to us. We can like look at some more models, or we can have like a working time where like we could actually just like, I can come around with everyone and like talk about stuff. And if people have things they want to show off, we can do that. So we'll sort of see what the week is like for the last week. Also, depending on what the Earth is doing, we might all be working from home and trying to hide away from the zombie flesh-eating virus. So we'll just sort of see how it goes. Also, I'll say, like, if next week they're like, the state of New York is like, you cannot be around anyone, we will just do this remotely. Like this class will totally work remotely. And like I said, we'll just set up more times to do one-on-ones together. I'm happy to like screen share with people and figure things out. Esteban and I were like have been like slacking back and forth at like 1:30 in the morning, and like we're both clearly night people. And I would say like we probably could have done that much faster in a 10-minute like video chat. It worked fine. Like I was happy with it, but it was But again, like it might be easier to do a video chat if people want to. Just sort of like let me know what you're up to when you have times.
If my data set is video based, can I use the same set for explain prediction and from StyleGAN?
Yep, yeah, you can. I actually think that'd be great because I think it's like helpful to see how different they are and what they learn between the two of them. So they will be very different. Cool. Everybody on the Zoom chat, how are we doing?
Good. Processing.
Okay. Let me know. So I'm gonna work with these folks a little bit more tonight, but let me know if any of you guys want to like do a video chat real quick to like look through stuff together, or just Slack me. Either of those work.
Sounds good.
Cool. All right. Cool. So I'm gonna stop sharing now, and yeah, I'll see everybody next week. If you want to take off, feel free. I'll hang out here for a little bit to help people as well.
Peace out.
All right. Bye, guys.